So maps are just the slightest bit trickier than sets, but they're also way more useful. Um, Sets are fairly limited, but maps are basically the most powerful data structure there is. So it's related to a set in the sense that it's almost like two sets. It is mathematically defined as this set of ordered pairs whose elements are known as the key and the value, and we use that notation here where we have the keys and the values. The keys is a set of unique things. The values don't have to be unique. But what we are doing with these maps is that we are creating a binding between a specific key and a specific value. So for instance, J gets bound or mapped to Jane. B and B2 get mapped to Bill. S gets mapped to Sam, B1 to Bob. And if we notice over here, the key J, Jane, B Bill, S Sam, B1 Bob, B2 Bill. So it is a many-to-one mapping. And it is also on-to, if I recall my terms correctly. Yep, on-to. In other words, everything in the value, that you don't get a value with that doesn't have a corresponding key. Again, that's the mathematics of it. But essentially it operates using these two methods, which we really haven't seen before, which is the put and get. Given a, I don't know why it says V there, but given a hash map, given a key, will return a value of type B. And you put things in the hash map by saying this is the key and this is the value. When I give you the key, you're going to return this value to me, right? That's what the get is. I'm going to say this key goes to this value. So one way to think of it is that maps are basically like lists, except for one big thing. The keys can be whatever you want. The indices are whatever you want. Also, there is no indices because it's not an order. We only have keys. But the keys can be whatever you want. But might be helpful to think of it at first like a list where you can just define whatever index. You can have index 0, 1, and foo. All right, what kind of keys might we be using? The keys are unique IDs, and it really depends on what your value is. So this is like the first use of maps, which is where we have something like this, where we have some unique identifier. And given that unique identifier, we can retrieve the value, which is all the goodies here, right? Maybe that's an array or a list. So the key might be an integer, a string, or another integer, and then the value might be list in these cases. It doesn't have to be a number. We can use whatever we want, again, for the key. So here, right, like if you're a university student and we want to retrieve your information, we don't ask you for your name. We ask you for a unique student ID number, right? Names aren't unique. I went to a middle school where I kept getting asked, hey, are you related to the Andrew Rosen who just graduated last year? No. He has the same name as you. It's not a particularly large school either. Same thing with your email. So we use your student ID number as that, because your name, your address, and definitely not your major or your GPA. These are all not unique things about you. Even your name plus birthday not guaranteed to be unique. So we issue a student ID number and associate all that stuff to your student ID number because your student ID number is unique. It's not because we just think of you as cogs in a giant faceless machine to extract value or to extract money from you in exchange for classes. It may feel like that sometimes, but I swear it has to do with data retrieval. Similarly, for an online store customer, right? If you're being asked to log in to Amazon or something, it asks you for your email address. That's unique to you. You can share a name with somebody. You can share an address with somebody else who has an Amazon account. Your credit card information might be shared between multiple people. And you want to keep that shopping cart information to yourself, right? Nobody needs to know that you needed to order 5,000 tennis balls and 1 ton of green corn. So, all right. So, part ID, similar thing over there. So maps, typically what we're going to use as the key is fairly unique. Doesn't have to be an integer. A lot of times it is. And again, just like the set, we have a hash map where we do the put and get operations in constant time. whereas the tree map will do it in log n time because it will use a binary search tree. Here are your methods. Notice that there aren't that many. It's a very powerful data structure, but just like the stack, it's very sparse in what it does. Size, how many maps there are, how many key value pairs there are. Is empty, tell if it's empty. Get, given a key, return the value. If you haven't put in that key, return null. Put, given a key and a value, please put that key value in. And if you, and here's the thing. If we already put that key in, then what we do is we update the value. We change the value. Okay? So, let's go, in a second I'll go ahead and pull this up in a separate video and do some basic operations to show you. Let's see over here. Remove. Given a key, remove the, given the key, remove the key value pairing that's in there. So I'll go ahead and boot up the command line and show you how that works.